Okay, Elaina, that was a 9-minute video, and I didn't seem to have any trouble uploading it, so I'll go a little longer version this time. And the thought occurs to me that we should try, like, if you have additional physics questions, we could try Skype or something. That might work. It's just finding a time when we're both free at the same time. That's probably the problem. Okay, so I was talking about the weight vector for the block on the inclined plane, and how whatever notation we use, we need to know what the components of that weight vector are in the direction or anti to the direction of movement, so what we're calling now the z direction, and then in the perpendicular to that direction, so the y direction. So I'm using subscripts, looks like your TA is using unit vector notation. Okay, so we're looking for the component of weight 1 in the z direction, okay, and that's going to be in the negative z direction, the down the plane direction. I'm focusing in on the right triangle here with a leg that is along the negative y-axis and a leg that is along the negative z-axis, and a hypotenuse that is the length of the weight, and then an angle that's not so clear in this triangle now, but an angle that is between the weight vector and the negative y-axis. So for the z component, I'm going to stick that negative sign in there because I know it's down the plane of, let's just leave it as weight 1, times sine of alpha. Right, sine because we're looking at the opposite side of that triangle, and then the y-axis gets a negative weight 1 cosine of alpha, where alpha is the angle of inclination. And then if we wanted to, we could go further and say that's negative m1g sine of alpha, and then negative m1g cosine of alpha. Okay, so we've got everything now tweaked into our coordinate axes, or coordinate system. The tension and the normal force are already there, and then S2 is going to travel in the vertical direction, so we don't have to do anything to its components. Okay, so let's try to slide that up, because the free body diagram is kind of like our map, right? The free body diagram is so important because it shows us what to do next. So the next step then is to apply Newton's second law to each of these two independent bodies. So like step 1, free body diagram, step 2, Newton's second law. And this follows the solution of your TA, right? There was step 1, deal with components, I think, yeah, and then step 2, apply Newton's second law. And as I mentioned in the very first post, your TA is using a double dot to indicate the second derivative of position, but I'm just going to go ahead and use A for acceleration. Both mean the same thing. We can say acceleration of body 2. If we're going to use our, I didn't really define, I guess this would be, no, I don't know what this would be, the y direction for block 2, never mind. I'm just going to call it A2. It could be like Y2 double dot, or whatever we call this vertical direction. I've lost track at this point of what the coordinate system is for. I just prefer to not even bother. So A2, the thing is that it all means the same thing. The notation is what it is, right? It's going to be highly like formal mathematical, or it's going to be maybe more descriptive, but it seriously just has exactly the same meaning. This is the second derivative of the vertical position of block 2, but we can express it as an X or a Y with double dots, or we can express it as an A. It means the same thing. So A2, acceleration of block 2, is equal to, since I've decided that the weight of block 2 is bigger than the weight of block 1, it's going to be equal to the weight of block 2 minus the tension, so that's the net force on block 2, divided by block 2's mass, like done, right? Acceleration is net force over mass. Yay, Newton. And then we do exactly the same thing for block 1, but we've got the funky coordinate system. So block 1's acceleration, and it's in a different direction because it's constrained to move on that plane, but it has the same acceleration because they're constrained to move together because of the, what word did you use? The non-extensible rope, right? So A1 is equal to the net force on block 1. And I neglected to talk about this earlier, but we expect block 1 to stay on the plane, so the normal force has to be equal and opposite to the, what are we calling, the y component of the weight. So these two forces are equal and opposite, not because they're action-reaction forces, but because the block stays on the plane, doesn't accelerate in the y direction. So then in the z direction, we have tension pulling up the plane due to the weight of block 2 minus the z component of the weight, right? I already assigned it a minus sign, which is m1g sine alpha. And then that net force needs to be divided by the mass of block 1. So we have Newton's second law. We use the free body diagram to sort out the masses, or rather to sort out the forces, and then we use that to inform our application of Newton's second law. It's all about Newton's second law for mechanics. So again, we are solving for both the acceleration of the blocks and the tension in the string. So at this point, we have two equations and two unknowns. We don't know the accelerations, and we don't know the tensions, right? And we're also not using numbers, so it's all algebra. Yay! So the other thing to say is the acceleration constraint, right? We're constraining these two objects to move together. So A1 equals A2 because of that inextensible rope. And T1 equals T2 because of that inextensible rope. So it all sort of falls together, right? So it's up to you as to which to solve first. We can say M2A equals, if I'm going to use M1G here, I should probably use M2G here. So let's go M2A, right? I multiplied both sides by M2 is M2G minus T. And then I can go M1A is equal to T minus M1G sine alpha. And if I'm going to solve for acceleration first, maybe I isolate tension here because that somehow looks a little easier. I don't know. So T is equal to M2A minus G. Sure, why not, right? And then I can substitute that tension. Wait, let me just check my algebra because it's Friday night and who knows what's going through my head. Nope, I flip-flopped. Just kidding. This is T equals M2 times G minus A. There we go. Now I've got my signs correct. And now this guy can be substituted into this. M1A is equal to M2. Oh, I shouldn't have bothered to combine those, but whatever. G minus A minus M1G sine alpha. I think I ran off the side of the screen there. I need to collect the accelerations if that's what I'm solving for. So M1A plus M2A equals M2G minus M1G sine alpha. A times M1 plus M2 is equal to M2G. I guess I could collect the G's. I might as well, but too late. I already wrote it in pen. G sine alpha. I hope that the algebra is like not an issue right now for you, but I'm trying to show all the steps, and I'm also just like working this out as I go. So on the right side, I've got a G. I can collect that. That's all I can do. So M2 minus M1 sine alpha on the right side, and I still have my A, M1 plus M2. So my final answer for the acceleration, given the algebra, and I'm pretty sure this, yeah, I'll just finish. So acceleration is equal to G times M2 minus M1 sine alpha, and the whole pile is divided by M1 plus M2. So now let's look at what your TA derived for acceleration here. Yeah, I think we're on point. Okay, so here's your TA's notation for acceleration, and here he's talking about the constraint, right? Whatever this letter is that he wrote, he's talking about double dot number 1 and double dot number 2. This is the acceleration constraint right here. We're saying acceleration of 1 equals acceleration of 2. I just wish I could read this symbol. I also don't really read or write cursive, so I'm totally not sure what that letter is. But we match, right? Our accelerations are equal. The two blocks' accelerations are equal, and they're equal to G times quantity M2 minus M1 sine, we changed notation here, alpha, or or theta, but that's the angle of inclination, divided by m1 plus m2. So we're good on the acceleration. And then once we know the acceleration, it's simply a matter of now solving for the tension, right? So we could take this quantity and plug it in here for acceleration, but that sure seems like unnecessary algebra. Let me just scroll up here and make sure I'm still in the screen and check my time. I'm at 10:20, so I think I'm okay. I'm going to keep talking. So I think I'd rather not do that algebra. I think I'd rather come back to my Newton's second law statement up here, right? Newton's second law for block 1 and block 2, and I think I'd rather solve for acceleration, right? I've got them, and then set the two equal to each other. So again, then for tension, we're saying A1 equals A2, and so we can set the two accelerations equal to each other. So A1 is weight 2 minus t. Darn it, I forgot to switch that into mg notation. Divided by m2, we'll do it in the next step. Equal to A1, which is t minus m1g sine alpha, divided by m1, and this is actually m2g. And so now we can solve the same set of equations essentially, except solving for tension instead of acceleration. And I hope it's okay if I can just go ahead and skip that algebra. The rest, as we say, is algebra, which may or may not be an issue, but let's go back to your TA solution, which is m1, m2 over m1 plus m2. So you can sort of see where the m1, m2 comes from, and then the m1 plus m2 is kind of similar situation here. And then I'm guessing now that's a g times 1 plus sine theta. So, I mean, I don't know. Do you want to see the algebra? I wish you could say yes or no to me. Let's go ahead and do this. So we've got m1 times weight 2, which is m2g minus t. And then we have m2 times t minus m1g sine theta. I'm like feel impelled to show you that whatever notation you take, we're going to end up with the same answer. So then we have m1, m2g, and then m1t, and then m2t, and m1, m2g sine, whoops, I forgot the s, sine alpha, and I'm collecting the t's and getting everybody else on the other side. So I've got t times m2, that goes over there, so plus m1, and then on the right side, I'm going to collect, hang on a minute, I'm flip-flopping myself, m1 plus m2, everybody came to the right. Now I have m1, m2g plus m1, m2g sine alpha. And now I can, let's see, what can I factor out here? I can factor out a g, m1, m2, and then I can say 1 plus g sine alpha. I thought I had a 2 in there though, so maybe I may have made an algebra mistake here that I'm not catching. I'm trying to work fast to not waste your time. But then we would divide both sides by m1 plus m2. So tension is equal to g, m1, m2, 1 plus g sine alpha. Divide all by m1 plus m2. And did I run off the page? No, but let's compare to the TA. No, there's not a 2. Oh, I remember when I first saw his handwriting, I thought that was a 2. Okay, so we're good. We're copacetic, right? So we've got m1, m2, g. That's all, multiplication. Who cares what's on top, right? m1, m2 over m1 plus m2. That's here. Then we have a g times 1 plus sine, what I'm calling alpha, and he's calling theta. All right, so we're good. We agree with the TA in terms of the conclusion. We disagree with the TA in terms of notation, but the notation means the same thing. Second derivative of position, whatever we're labeling as position, means acceleration. We can either use subscripts. Where did my subscripts go? We can either use subscripts or we can use unit vector notation. So I guess if I'm going to call this y and z, instead of calling it weight 1z, I guess I could call it like weight 1 z hat. I mean, that would work too, right? I'm just trying to be really clear, either with unit vector notation or with subscripts. I'm trying to just say the same thing, which is that this is the component of this vector in this direction, right? That's the big deal. We want to be clear about what we really mean. So in any case, there's that first problem. I'm going to stop and post this, and then I'm going to look at that second problem where we don't ignore the pulley, and then we have to pull in like rotational issues. Yay, this is fun. Thanks for emailing me.